Hello students, welcome to the lecture on differentiation, and after the lecture we will be able to learn the following objectives. Define derivative, explain the derivatives of some difference, understand product and quotients. Let's start with a brief introduction to differentiation. Differentiation is a method to compute the rate at which a dependent output y changes with respect to the change in the independent input x. This rate of change is called the derivative of y with respect to x. This is a technique used to calculate the gradient or the slope of a graph at different points. The most common approach to turn this intuitive idea into a precise definition uses limit, but there are other methods such as non-standard analysis.
Differentiation is one of the major parts of calculus. I'm going to demonstrate some of the basic rules that you need to differentiate by starting with a simple function, y equals 10x squared. First, I'm going to plot a graph of just roughly what the shape of this function looks like on a set of xy axes, and you'll see soon how this comes into play with differentiation. So y equals 10x squared graph sort of has a curve sort of like this, which I've just labelled. Now, y equals 10x squared allows you to plot the graph. However, there are a lot of other things about a line you sometimes want to know. For instance, the slope of the line is often interesting. So where I'm putting these crosses, I'm also drawing a line which is showing the slope of the function at those points. And this is one of the many things you can use derivatives for, or differentiation. So first of all, we need to know one of the basic rules of differentiation, which is if we have a general function y equals a, some constant a, times x to the power b, then the derivative of this function, which I'm going to use a y dash to indicate that I'm calculating the derivative, is you put the b out in front, multiply it by the a, multiply that by the x, and then reduce the power of the x by 1. So for our particular function, a equals 10, because that's the thing in front of the x, and b equals 2, because that's the power x is raised to. So what we're going to do is use this rule to work out what the derivative of y is in this case. So y dot equals, or y dash, equals b, which is 2, times a, which is 10, times x, and we reduce our power of x by 1. So it's going to equal 20x to the power 1. Now anything to the power 1 is just the same thing again, so 20x is our answer. Now, say we wanted to find the slope of that graph we've just plotted at a certain point, say at x equals 4. Well, we can use this derivative we've just worked out and sub in 4 instead of x. So, the derivative of our function at 4, which is what I've done with the brackets there, is 20 times x to the power 1, which equals 20 times our value of x. Now I'm just rubbing out the power of 1 because we don't really need to indicate it. 20 times 4. And 20 times 4 is 80. So the slope of our graph is going to be 80 at x equals 4. So that's one of the many uses you can use derivatives for. So that's not the only rule of differentiation there is, but I'm going to practice a little bit more with it first to get comfortable. So here's another function, y equals negative 3 x to the power negative 4. Now, to find the derivative of this, we take the negative 4 and put it out the front, multiply it by the negative 3, multiply that by the x, and we reduce our power of x by 1. So negative 4 minus 1 will be the new power. So y dash equals negative 4 times negative 3, which is 12, x, And negative 4 minus 1 is negative 5, so that's our answer for the derivative, 12x to the power negative 5. So let's keep going, and here's another very simple function, y equals 10. Now notice first of all that there doesn't seem to be any x's on the right hand side of this equation. What we can do, however, is by remembering that anything to the power 0 is 1, we can write an x to the power 0 on that side, because since x to the power 0 equals 1, y equals 10 times x to the power 0 is just going to equal 10. So now we can use that same derivative rule which we've used before. So y dash is going to equal, well, we put the 0 out in front, multiply that by the 10, multiply that by the x, and we reduce the power of x by 1. Now this is pretty simple. When you multiply anything by 0, the answer is 0. So what we've just shown is that when you find the derivative of a constant, which doesn't have any x's in it or anything, the answer is 0. What about when you've got more than one term in your equation? So here we've got 2x squared plus 3x plus 4. Now 3x is like 3x to the power 1, so I'm just putting that in there to make it a bit easier. So when we derive this, the 2 goes in front of the other 2, the power of 2 reduces by 1, the 1 goes in front of the 3, and the power of x reduces by 1, and the 4 is a constant, so it just is 0. So if we multiply this out, we've got 4x to the power 1, which is just x, plus 3, because we've got 3 times x to the power 0, which is just 3 times 1, which is 3. What about when we've got sine and coses in our equations? Well, if we have a function y equals sine x, the derivative of y with respect to x, which we can show by a y dash, is just cos x. So the type of function just swaps over. However, when we have a function y equals cos of x, our derivative of y is actually negative sine x. So when you derive sine x, it becomes cos x. When you derive cos x, it actually changes sign and function and becomes negative sine x.
Now we will know about derivative. We shall need to find the value approached by delta y by delta x as delta x tends to 0 in many different situations. There is a special notation used to signify the process, like limit notation. Let y equal to function x so that delta y equal to function x plus delta x minus function x. Then the value approached by delta y by delta x when delta x tends to 0 is denoted by as shown on the screen. The result of the process which is shown on the screen is called the derivative of function of x. The process is called differentiation. Derivative, slope and tangent. Let y equal to function of x and delta y equals to function of x plus delta x minus function x. Then the derivative of y respect to x signified by as shown on the screen.
Okay, we want to do a little bit of work with derivatives. Let's find the derivatives of some functions here. First I have f of x is equal to x squared plus 3x minus 4. Nice simple polynomial. I'm going to differentiate this. But first let's talk for a second about notation. If I was to say that this was y equal f of x equal all of this, then all of the following represent the derivative of y with respect to x. I could say dy dx. That's the derivative of y with respect to x. I could say the derivative of f of x with respect to x. That's also the derivative of y with respect to x, or of f of x with respect to x. I could say that this is f prime of x. When I do that, I know that when I just use the little prime mark, I know I'm differentiating f with respect to x. And I could also just write down y prime. And then there's no mistaking y as a function of x, so when I say y prime, I mean the derivative of y with respect to x. So whatever these are, when I differentiate, let's go ahead and do that. The derivative of a sum is going to be the sum of the derivatives. So that tells me I can differentiate each one of these terms separately. So I'll differentiate x squared with respect to x using my exponent rule. I get 2x. Plus, I differentiate 3x with respect to x. Well, I have a constant times a function of x. So when I differentiate, it's that constant times the derivative of that function of x. So 3 times the derivative of x with respect to x, which is just 1. So I'll just write that as 3 minus the derivative of that constant, which is 0. So there's my derivative, 2x plus 3, and I can use any of these notations right here to represent it. Let's look at our next problem. V of r is equal to 4/3 pi r cubed. Well, if I want to differentiate this with respect to r, so I'll just say v prime of r, meaning I'm differentiating v with respect to r. So here I have a constant, so this is a constant times a function of r. So when I differentiate this, it'll just be that constant times that derivative of that function of r. So I have 4/3 pi, and then I differentiate r cubed with respect to r, and I'll get 3r squared. That's my exponent rule. Now I can simplify this a little bit. I'll just divide out those 3's right there, and I end up with 4 pi r squared for that derivative of v with respect to r. Let's go to a little farther here and do a couple more. All right, I want to differentiate f with respect to x, and f of x is equal to 16x to the third. A couple different ways to do this. You could simplify this first and make it 16 to the third times x to the third if you wanted to separate those, or you could just use the chain rule. Let's just differentiate. I'll have f prime of x is equal to, okay, I have some function of x to the third power, so it's 3 times 16x, that's that base, to a power 1 less 2, and then I have to differentiate the base, in which case I get 16. So I have 3 times 16x quantity squared times 16, so I have 16 times 16 squared, 16 to the third times 3 times x squared if I want to simplify that. But right now what I want to do is just take you through and let you look at the derivatives. We don't have to simplify that one. Y of t is equal to 6t to the negative 9. Okay, so I'll take y prime of t, meaning I'm differentiating y with respect to t. Now I'll differentiate here. I have a constant times a function of t, so I'll just have 6, that constant times the derivative of that function. Now when I differentiate t to the negative 9, it's negative 9, t to the negative, okay, I have to subtract 1 from that exponent, negative 9 minus 1, negative 10. So here I have 6 times negative 9t to the negative 10. Let's just simplify that one. 6 times 9, 54. Positive times negative, negative, so negative 54. T to the negative 10, so how about 54 over t to the positive 10th? Did that go off there? Yep. And so there you have negative 54 over t to the positive 10th. Yeah, you know, if you left it negative 54 t to the negative 10th power, you know, that's okay. It's still the correct derivative, but a lot of times instructors like you to write your exponents as positive numbers. So you have to see what your instructor wants you to do.
Here we will talk about the rate of change. The quantity limit delta x to 0, delta y by delta x is usually needed to solve problems which have no immediate connection with the slope of the graphs. This idea was only introduced to give the reader a picture to hold on to. Moreover, it is not always appropriate to call the variables x and y if other letters arise naturally. For example, a car is moving along a straight road represented by an x-axis, and that time t its displacement, which may be positive or negative, from the origin is given by x equals to function of t. We can deduce the velocity from moment to moment from this information. Choose any moment t and suppose that between times t and t plus delta t, the car moves from x to x plus delta x. Then delta x is given by shown on the screen. The quantities delta t and delta x could be imagined as being recorded with a stopwatch and distance meter, and average velocity over the interval delta t is shown on the screen.
Okay, in this video I'm going to talk about what is a differential. What does dy dx actually mean? This video leads on from the video on what is a function. So have a look at this video if you haven't already before you actually watch the video you're watching now. So in the video about functions, we said we could have a function y and it could be a function of X, Z, A. We said that these were the ingredients to make Y. We said, for example, we could have breakfast being a function of milk and Frosties, like that. So we said B is a function of M and F, like that. So that's the first thing. Next, what does differential mean? A differential gives you a slope or a rate of change. Right, a slope or a rate of change. Oh, what's a slope? Okay, well, let's just draw a very quick x and y axis, or xy plane, Cartesian plane. Say I have a function like that, that's y equal to a function of x. Alright, now a slope would be how quickly it's changing, and usually you have a slope by having a tangent on it. Now I'm not going to go into describing all these things, but the slope would be the slope of your tangent, a tangent line. So it might be here, wherever it is. So by computing the derivative, you will get the slope. That's the first thing. What else? It will give you a rate of change. So that's what slope is. Slope is a rate of change. Well, like, let's look at this. If I draw a tangent here, it's pretty much straight, right? That's fine. So you might have a certain amount of whatever that slope is there. But here the slope is different, therefore the rate of change is different. Here the slope is different, so therefore the rate of change is different. Now what do we mean by the rate of change? We mean how much is one variable changing when another variable changes. So say if we have y is equal to a function of x, y is equal to 2x. Okay, so if I go x is equal to 1, that means y is equal to 2. X is equal to 2, y is equal to 4, like that. So every 1 unit I change in x, I change 2 units in the y. For every 2, so that's what that means. So its rate of change is 1 unit, 2 units in the y for 1 unit in the x. That's its rate of change. Like for example, you would say the rate of change. Let me think now. The rate of change. What else changes? Speed. For example, if you're speeding up, if you're accelerating, your speed is changing. So at one moment, at 0 seconds, you might be at 5 meters per second. At 10 seconds, you might be at 10 meters per second. At 100 seconds, you might be, I don't know, 100 meters per second. Now, the rate of change would be how quickly are you changing, is your speed going up with your time? That's what the rate of change is. And if you graphed this one here, let's go ahead and see if we can graph that. Okay, I'm going to say this axis here is time, this one is velocity. Alright, so at time 0 we're at 5. We'll say this is, let's say that's 5. So we're here. At time, you can see that. At time 10 we're at 10. Where are we? At time 10 we're at 10. And at time 100 we're at 100. Like that. That's not supposed to be a straight line. I'll do that again so it's not a straight line. Okay, and there's my graph. And now what's the rate of change? How quickly is your speed changing with time? And you draw this graph, and you might want to get the slope of it. You draw a tangent line, and you'd get, you'd use the slope formula, y2 minus y1 over x2 minus x1, and that's m. And you know what that is? That's a big pain. Nobody likes doing that. That's just an utter pain. So what we do instead is, to be honest, nobody in the real world will ever compute y2 minus y1 over x2 minus x1. Maybe a computer will do it for them. Instead they will use something that looks like this. d something. So how do you read it? You read this as dd, right? So for example, we'll say this. This would be d dx, d dy, d dz. That's what that means, okay? What about this? I'll tell you what they mean in a moment. dy dx, dz dA, dB dA. That's how you read them, or you'd say them. So first of all, you'd read this as dDA, okay? So that means the rate of change of something I haven't written with respect to A. So say y is a function of z, a and b, like that. And if I want to find how quickly is y changing with respect to A, well then I'd go dy dA. If I want to find how quickly y is changing with respect to z, I would say dy dz. If I want to find how quickly y is changing with respect to b, I'd say dy dB, like that. dy dB. What if I had r is equal to a function also of z, a and b? So I would say, what if I want to find out the rate of change of r with respect to a? dr dA. That's what that means there. dr dA, the rate of change of r with respect to a. How quickly is r changing as a changes? Okay? So they're the variables, they're the ingredients, and this is the actual one itself. Now there are different ways of writing a differential, and I'll just show you them here. You might see loads of these different ways. You could say it's if I want to get ddx of something, that's the rate of change of something with respect to x. So you could write this, we'll say dy dx, okay, that's also equal to d dx of y, like that. They're the same thing, or you have, we'll say y is equal to 2x, you could have d dx of 2x, or you could have d 2x dx. They all mean the same thing, where we'll say in this case y is equal to 2x, like that. So the rate of change of y with respect to x, the rate of change with respect to x of y, that's the same thing. If y is equal to 2x, you say the rate of change with respect to x of 2x, the rate of change with respect to x of 2x, like that. So it means the rate of change or the slope. So you'll be using it in things like acceleration, velocity, and so on. Now, look, just finally to show that these give you something real. This isn't something airy-fairy that you learn in school and never use. These things have a physical meaning. For example, we'll say position, and I'm going to say x means position, okay, and time equals t. Now the question is this: what is the rate of change of position with respect to time? Oh, I'll tell you the answer. It's speed. So dx dt is equal to speed equals v. What about the rate of change of v with respect to t? The rate of change of velocity with respect to time gives you acceleration. Now, I don't expect you to understand that. What I hope you take from this is that differentials have a physical meaning and they're used everywhere. Rates of change. The rate of change of your stock prices with respect to time. That'll give you something. The rate of change of growth with respect to time. They're not all with respect to time, but if you're talking about something physical and real, you're often talking about rates of change with respect to time.
Let's talk about derivatives of sum. If c is constant, then derivatives are shown on the screen. If a, b, c are constants, then derivatives are written on the screen. Now look at the derivatives of difference. If c is constant, then derivative of difference is shown on the screen. If a, b, c are constants, then the derivatives of difference is written on the screen. Let's discuss about the product line. It is appropriate to use this rule when we want to differentiate two functions which are multiplied together. For example, y equal to e to the power x sine x is product of the function e to the power x and sine x. In the rule which follows, we let u stand for the first of the function and v stand for the second. If u and v are function of x, then look at the equation written on the screen. Now we will talk about the quotient rule. It is appropriate to use this rule when we want to differentiate a quotient of two functions, that is, one function divided by another. For example, y equal to e to the power x by sine x is a quotient of the function e to the power x and sine x. In the rules which follow, we let u stand for the function in the numerator and v stand for the function in the denominator. If u and v are functions of x, then to find the quotient rule, look at the equation shown on the screen. Now in the end, let us summarize what we have learned in this lecture. The process of finding a derivative is called differentiation. The rate of change is called the derivative of y with respect to x. The derivative of f collects all the derivatives of f at all the points in the domain of f. At an inflection point, a function switches from being a convex function to being a concave function or vice versa. A vector-valued function yt of a real variable sends real numbers to vectors in some vector space R.